So we're taking a look now at equilibrium supplementary problem number 26. We're being asked to consider a reaction. 1 mole of reactant A decomposes to produce 2 moles of B and 1 mole of reactant C. These are all gases. We're told that 1.00 moles of substance A is put into a 4-liter flask at a given temperature. We're also told that concentration of substance C at equilibrium is found to be 0.050 molarity, and we want to find the equilibrium constant Kc for the reaction. When we read the question, we want to highlight a few things. A few things should jump out at us. Number one, we realize that we're being told the moles of reactant A. Whenever I see moles, I realize I'm probably going to have to switch that to a molarity in an equilibrium problem, and that means I want to look for a volume, and that's where this 4 liters will come into play. So moles divided by liters will give us a molarity. But then I look further in the question and I realize that the substance C is mentioned, and it tells us its concentration as 0.05 molarity. So we realize that they're telling us here a little bit tricky. They're giving us the moles of reactant A in a 4-liter flask, but then for substance C, instead of also telling us moles, they're telling us the molarity. So we'll keep that in mind as we solve the problem. So what we want to do is start a new page here, and we will start the equilibrium answer by writing the balanced equation again. So A decomposes into B and C, and we were told we're going to set up an ice table to solve the problem. Okay, we're setting up the ice table because the question told us the starting conditions when it said that 1 mole of A is placed into a flask, and then it mentions equilibrium conditions when it tells us the concentration of C at equilibrium. So because it's telling us both starting and equilibrium information, we're going to use this table, which tells us the initial, the change, and the equilibrium conditions, just organize information. So the initial concentration of A, we want to use molarities, will be 0.25 molarity. If you're wondering where I got that, we used some grade 11 chemistry. C equals N over V. To find concentration, molarity, you take 1 mole of A and divide by 4 liters, and that gives you 0.250 molarity. The question said that the A was placed in the container, and it didn't even mention the B or the C at the initial stage of the reaction, so we'll assume that they were both 0 initially. The question does say, though, that at equilibrium, so we're going to jump down to the 3rd line of the table, the equilibrium line, the concentration of C was 0.050 molarity. So 0.050 molarity. We can now finish the table because we know the starting and the equilibrium amount of substance C. We can see that it must have gained 0.050 molarity. Since it started with 0 and ended with 0.05, it must have gained 0.05. The product B must also have gained, because all products will gain at the same time, and reactant A will lose because it's on the other side of the equation, it's going to be losing. Remember that everything on one side either gains or loses, while everything on the other side of your equation will do the opposite on the change line. We can fill out the rest of the numbers in the change line by looking at the stoichiometry. 1 mole of reactant A reacts while every 2 moles of B are produced, and 1 mole of substance C is produced. So looking at those ratios, we notice that for B and C, there's a 2-to-1 ratio. 2 moles of B for every 1 mole of C. So therefore, B must gain twice what C gained. So 2 times 0.050. 0 plus that will give me 0.1 molarity for substance B. For substance A, the ratio is a 1 mole of A for every 1 mole of C, so now it's a 1-to-1 ratio, so it will lose the same amount that C gained, 0.050. So 0.25 minus 0.05 means we have 0.200 molarity of substance A at equilibrium. We can now jump in and solve the problem. We're wanting to find Kc. Kc, we'll write the expression, concentration of B squared, because the coefficient of B is a 2, times the concentration of C, and divided by the concentration of A. We remember products go on the top, multiplied, and the reactants go on the bottom, multiplied. In this case, there's only one reactant. We take the numbers from the equilibrium line of the ice table, and we're going to calculate Kc. So for B, it was 0.1 molarity. You have to square that, times C, 0.050 molarity, and divided by A, which was 0.2 molarity. Don't forget you need to square the concentration of B. Pick up your calculator and you evaluate this, and you find that Kc is 0.0025 molarity. I'm sorry, 0.0025. The units for Kc are not normally included because they change. In this case, if we did include units, it would be a molarity squared if you look carefully at that. But you're generally not going to put units with Kc, so you just leave them out. You could, of course, convert the answer to scientific notation, in which case it would be 2.5 times 10 to the minus 3. Before you leave the question, you might want to ask, is it reasonable to get such a small Kc? You could get much smaller values, but that's still a pretty small value for Kc. When we think about it, we began with 0.25 molarity of reactant A, and we lost 0.05 molarity. So we lost 1/5 of what we had, or 20%. When you're losing just a small amount of reactants, Kc should not be very big. Kc should be small. So it makes sense that Kc here is 2.5 times 10 to the minus 3, a pretty small number, because we were only losing 20% of our starting reactants.